to see you here today, that many people interested in Haskell and especially in type classes. So I'm Paweł Sączawa. You can contact me by my email or by Twitter. These are the data required. So today I would like to talk about type classes concept originated from Haskell. I would like to say a few words. Why shouldn't we even bother to learn about this stuff, and why do we need another type of classes? So moving forward, I think it's quite useful to read history of Haskell paper written by these four guys. It answers few questions: why it even began with Haskell, and why we needed a new type of classes and polymorphism. So there was a lot of going on in functional languages in the 80s, a lot around the world in academia institutions. So like they had a lot of new languages, functional languages, that they dealt with the same problem, but in different ways. They didn't have one common language. So as we all know, if you have 10 different standards, you should develop the 11th one to unify them all. So they decided to do it, and actually it worked for them. They formed a work group which was supposed to develop new functional language, which was supposed to be modern, all that funky stuff like general purpose, static typing, and so on and so on. But they had one quite hard requirement for the new language. They couldn't use subtype polymorphism, and it was really hard for them. They decided to do it because they already knew that subtyping is quite complex, and it brings a lot of problems, like the diamond problem. I hope we all are familiar with. So they had this big trouble with that. So they had a language which was completely useless. Although Simon Peyton-Jones, one of the creators, say that Haskell is still useless, so maybe not that much changed since then. But yeah, so they worked on that, and Philip Wadler came with the idea of type classes. He proposed this on mailing list 24 February 88. So yeah, I've heard that he came with idea because he misunderstood a question that his colleague gave him, and because of this misunderstanding he came with type classes. He published with his colleague Stephen Blood a paper about ad hoc polymorphism titled "How to make ad hoc polymorphisms less ad hoc." So they had this concept about a new kind of polymorphism, which we already have template polymorphisms, like when we have templates in many languages, or it's called, of course. So, and the other kind is ad hoc, which means that functions behave differently for different type. So following, I would like to introduce some basic Haskell to be able to talk about type classes. So first of all, we have to be able to define new type. This exactly means that we have type foo, which can take two values, bar and bus. These are only two types that we are concerned about right now. And following that, how we work with this. So as we can see, we can ask the REPL GHCI about type of value bar, and it answers us that that's type foo. Following, we have how we work with the types. We define a function that, for example, takes type foo and returns string, and as we can see, using just plain pattern matching common in functional languages, we can return exact value for this. So defining new type classes, like the simplest possible one, we can define class toString for type A, not given right now, using word where, and we define that toString takes value of type A and returns value of type string. And following, we have to define an instance for the type we want to work with. So instance for our foo type, we might define it the simple one, like it just returns always foo to string, not taking in concern the value. And how we deal with this is like when we call function to string with value of type foo, it just finds the exact function body and executes it. So and in big picture, it's all about type classes. Of course, we can move to more interesting stuff. So having few example type classes built in Haskell, we have type class show, quite common used. That is how it's defined. We have to define function show that takes the type and returns string. Example instance for our type foo is given here, and yes, we use this this way. So but what if we add new values to our type? It may be not funny task to define this, and it may be error prone, and it smells like boilerplate. So following even further, like we can take the integer type, and integer type in Haskell maybe define like our data foo with all the values just in constructors. So it wouldn't be possible to define a show type class for integer. So for that we have something like a type class derivation. Instead of defining every possible value, we can just derive show, and the compiler does the work for us. And this code is exactly equivalent to this code. Another few examples of basic type classes in Haskell. So these are EQ, odd equals, ordered, show we already talked about, and enum from enumeration. Thanks to having derived instance of type class EQ, we can check for equality of our values. then we, thanks to having instance of ort type class, we can check if it's smaller. And thanks to having unknown type class, we can use built-in function like successor and even defined ranges that takes the order that our values was defined in data definition. Maybe I would like to talk now about quite common type in Haskell, which is maybe. You may all know this from Scala. It's equivalent to option, and it's defined this way in Haskell. So we can see that data maybe from type A is just nothing or just n value. We can use this instead of nulls from traditional imperative languages. So we never have null, just nothing, like we didn't find anything in database or something like that. So, but maybe it's not a type. It's not exactly type, because as we can see, just takes some value of type A and then returns type maybe of A. So maybe as it is, does not have type, type of just from X, just with X, have type of maybe car. So we can always ask for type of maybe, and it's exactly kind. We asking about kind because this is this lives in types area, so it's not a value. So we ask about kind of maybe, and it shows us that it takes some type and returns another. And as we can see, kind of maybe car has only one star, a placeholder for a type. So we call it that maybe data maybe, exactly this part, just maybe it's type constructor. So it constructs exact type after applying some type to it. And in the right side of the equal sign, we have value constructors, which are nothing and just from A. Following. Right now I'm going to talk about one of quite basic type classes in Haskell, which is functor. Everyone who tries to do some stuff in Haskell has to be familiar with this. So it's defined this way: class functor from f. It has function fmap, which takes a function from type A to B, then takes value of type fa and returns value of type fb. Why I want to talk about this is this exact part, because the compiler, when analyzes this, it sees that f, it's not just a regular type, it's actually a type constructor. So as I said, it may be maybe type or kind, so it's not just every type, it has to be defined type constructor. The following, it's the exact implementation from instance functor for maybe, where we have, when we map on nothing, we always get nothing, and when we map on some value just A, we can get the function applied to the inside value. So that this thing looks quite interesting, because when we look long enough about this, we came to conclusion that there is no other way to define this instance. So few smart guys actually has proven that mathematically proven that it's the only way to implement this, and then they introduce some new extension to Haskell language, JC actually, and we do not even have to write this for our maybe data type. Thus we introduce Haskell language extension, and we can say that it derives from functor, like we derive from show and equal and ordering. Actually, it brings us more less code and less places we can make mistakes. So following that, we have subclassing of type classes, we may call it. So it means that when we want to define class ord from ordering, we have to have defined equals for that data type previously. So it means that if we want to derive ord without equals, we will get compiler error. So if first we have to define equals, and following we have class constraints maybe again. So we can say that we can check for equality of values, maybe values only when the inner value has defined equal type class. It's quite logic to introduce that constraints. So type class good part. We do not have subtyping. It's much less complicated. If you look at Haskell, it's really small language. It's actually easy. Maybe not to program in, but at the beginning, but it's really small. There is not that much to learn at first glance. And we do not have this kind of problems like the diamond problem. It's easier to define some notions like equality, ordering. We like in Java we have this common ancestor for every object that have defined equality and hash code, I believe. So it only brings trouble for us. Thanks to type classes, we can put a lot of constraints in function about the types we work on. So it really works well with our type safety. And last one, we can define instances for types that we do not control, like when you work with some library and you do not have access to the sources, you can still work with this and new type classes. Bad parts, I would like to say that there is none, but we all know that there are no silver bullets. First of all, type class definitions are restricted to the top level of the program. Some people even say that type classes definition breaks the whole pure functionality, because when we define it and we import it to our program, it has side effects, so the program behaves differently, and yeah, they say that it's some kind of side effect about in the type word, but this exact thing means like with this example we have built-in class monoid, which is quite common. We all know this from basic algebra. It means, for example, with integers that we can always add to integers, and the result will always be integer, and we have the empty value, which in adding is 0 and in multiplication is 1. But now we have the problem. Example instance for list in Haskell is where we have empty value as just empty list, and append there is list concatenation, and it's quite obvious and it works really well. But moving forward we have this problem. We have integers like all numbers, and there is no such thing as natural monoid for this, because we always have multiplication with 1 and addition with 0. So what should we choose? Haskell deals with that by defining new types. This is example with product, which means we choose the append as multiplication and empty as 1, and it's defined. This coerce function helps us with dealing with boxing the value to the other type. Don't worry, it's not boxing like in Java. It actually has no runtime impact. It just lives in compile time. Some people say that it's not that big a deal, this problem, because they actually want to introduce this to Scala. So like on regular day they say that Scala is better because it has no it doesn't have this problem, but they want to introduce it because like it's get worse. For example, when we build two sets with different ordering defined and everything is fine, but what if we want to merge those two sets? Which ordering to choose? So that's a case when really nasty bugs can occur. So some people say it's a problem, some people don't, but maybe it's just common sense, best to choose here right now. And the last problem I'm aware of are heterogeneous data structures in Haskell. It brings existential types. What are these heterogeneous data structures? We can compare this to lists in traditional imperative languages like Java, when we have list of some objects, but we can actually put object from some subclasses. Of course, I think we have to put some wildcard on this or something, and because of no subtyping in our value word, we can do it in Haskell. So this is commented out, so we can have some data full with two types and AB, and it has only one value, which exactly two values of type and AB. And what if we would like to add a constraint that A can only be of type that has instance of typeclass show. So for example, we can only define this on function definition on this level. So so we can deal with this. So this is some fun that takes value of type foo, a, and I chose string because why not? But we have to say that we say here that a is any type that has instance of show right now. So it just some constraints on the type, and we can deal with this problem the other way. So yeah, what if we wanted to say that the foo and a is only of show, has to have instance of show? We do not have any way to define this. So they introduced the existential quantification, which means that data foo it's quite similar to this, but takes only b and has one value bar with values a and b, but we say that for all types that have instance of show a.
I have a question. So why is it called existential when we say for all? There are two quantifications, existential and universal. One is for all and one is exists.
Yeah, because this say for all that there exists that proof that there is instance. We say that there has to be a proof for every type A. There has to be a proof that there exists instance of type show. So yeah, it's mashup of exists and for all, but it actually means that there is proof for every. Yeah, there exists a proof for every. Okay, so we can deal with this. Now we can use this way, and we always know that there is value a that has instance of show. And addressing your question once more, that we know typeclasses are kind of polymorphism that only lives on compile time. So it's not runtime like we have whole subtyping and we decide on runtime which exact body to execute. And this is the way I try to define some function that would return some type A that always have instance of show, for example, and the compiler won't let us because it does not have the proof that for every A that it would like to deduct the type, there is no evidence that for every type there will be the instance for this. So yeah, that's quite important thing, that it's compile time polymorphism, and it's actually quite similar to method overloading. I believe it's even done by quite similar way. And one nice thing about this is this polymorphism works on many types, like when we have subtype polymorphism like in Java, it only varies on the type of this. I think we all are familiar with the concept that in Java or something like that, there is always this pointer which the implementation varies, and in Haskell we have to the implementation actually varies on types of few arguments to the function, but it's really I think, more philosophical stuff than actual problems. And the response from Java is, I think, it's visitor pattern, something like that. So that's all I wanted to say. I just, as it was in the talk description, I'm complete beginner in Haskell. These are things I learned when I played with Haskell and typeclasses, and actually I do not have any single line of code on production right now yet, I hope. So yeah, you have to double check everything I say, because I believe till you have production code, you know nothing about the language. So that's all from me. Thank you.
Can I have a question?
Of course.
Could you come back to the slide where you said that derive factor typeclass?
No.
Yeah, so can you use this construct for any type, or is it just restricted to mainly?
No, it's quite
I mean, I know you can use deriving show or equal to any type, but this special deriving factor can use any other data type other than maybe.
I'm glad you asked. So you can use it for every type. So
does the compiler know how to implement that type class?
Yes. So when we check, maybe how to say it, when you have how is it called, that I'm missing the word, template polymorphism is generic. So let's call it generic, that the function has the same body for every type. So I'm not an expert, I'm not a mathematician, but they have proven that because of the functor definition and maybe definition, it has to be generically polymorphic for inside type. So they have proven that in this instance, in this example, that it's the only way they can implement this, and it actually holds for every algebraic data types. That's the only kind of types we have in Haskell. Yes?
So I think you should mention that there is possible another implementation of this functor. I can show it right away. In the second line, it say that fmap equals nothing.
Yes,
both
but it wouldn't be generically polymorphic.
Well, so maybe you should explain what that means.
So it's not that simple, but it.
There are some axioms of the functor that are not written on the slide right now.
Yes, but I didn't want to.
They prove that there is only one way to do it correctly. Depends on the axioms of the functor type that are not part of the that they are not part of the language. It's part of the wider theory.
Yes, exactly.
Of the category theory.
That there are the three theorems. I believe it's based, or at least it's related to three theorems. I'm not sure really, but it comes up when they talk about it. So yeah, it works for every data type we have in Haskell. We can define. And they introduce this also for traversable and foldable when they came with idea of proving this, it's possible to build an algorithm that will always produce some proved and actually working implementation. And they went even further with applicatives and so on, but it's not, for example, deriving applicatives, it's not always possible for every algebraic data types, and as far as I know, it's not possible in Haskell GACI right now, but Scala guys in Scala Z or Shapeless already do it, so it's possible, but for only some subset of data types. Yes, and as you said, this is quite more complex concept, and it requires more with logic and type theory and category theory to come with these things. So, as I said, I'm still a beginner, and it's a talk from beginner to beginners, and actually it's enough for me to know that there is a proof, but I'm not a mathematician, and I do not want to even understand it, or even worse, memorize. So, any other questions? Maybe simpler?
Yeah, you had a product type class that
Yes.
you were writing an instance for, and you had this function called coerce.
Yes.
And you said that it's a compile time. You talk about boxing.
Yes.
And that it's not the same as boxing in Java. I don't know what boxing in Java is, because I don't do Java. But you said that it's just a compile time thing, and that there's no runtime penalty. My experience with boxing or unboxing values in Haskell is for the runtime performance advantage of forcing strict evaluation. Is that a different thing that you're talking about?
Yes, it's different. It was, I think, here, right? So this means that you have only one data constructor, which only introduces us a new type, which is quite similar to data definition. Like if we only have to here data, it wouldn't be so fast, because every time we would be creating new value just with box.
Type has no runtime performance.
Yes, exactly.
You didn't mean the coerce thing. Maybe I misheard you.
Coerce is just a function that magically allows you to cast between the inner type and the box type. Like,
oh, so by box type you mean the A in num A?
The product is the
Product.
It's some way to type.
Oh, okay.
This type it's not,
Yeah, right.
not the basic A type.
Okay.
do not ask how the coerce works, because I have no idea at the moment. Some funky data and type theory, I think so. Any other questions? Thank you.
Is it finished?
Yes, I think.
Well, thank you very much. I think